And welcome back. As we continue our cosmic journey and look at Earth, we had previously talked about our atmosphere, and we talked a little bit very briefly about how Earth's atmosphere has changed and some of the origin of that. But let's go ahead and take a deeper look at that through how that atmosphere might have changed due to the various processes and evolution of our life forms throughout its history. So one of the things to remember is that the sole existence of life is very dependent upon the condition in which it can live in. As far as we know, Earth seems to be the only planet in our solar system that has life. Now, the origin and development of life are an important part in our planet's story. Life arose very early in Earth's history, and living organisms have been interacting with their environment for billions of years. Obviously, some of that life was very simple in the beginning, but it gradually became more complex over time. And we recognize that life forms have evolved to adapt to the environment on Earth, and we're now beginning to realize that Earth itself has been changed in important ways by the presence of living matter. And the study of this coevolution of life and planet is one of the subjects of the modern science of astrobiology. So let's talk a little bit about some of the origin of life. Now, the record of the birth of life on Earth has been lost in the restless motionless crust, because remember, our crust is constantly recycling itself. According to chemical evidence, by the time the oldest surviving rocks were formed about 3.9 billion years ago, life had already existed. At about 3.5 billion years ago, life had achieved the sophistication to build large colonies called stromatolites, a form that's so successful that stromatolites still form on Earth today. As we can see here in this rock, this structure that you're looking at. Now, few rocks survive from these ancient times, and abundant fossils have been preserved only during the past 600 million years, which is less than 15% of our planet's history. So if we want to really try and find some older rocks, it's very hard, again, because remember, plate tectonics, one of the side effects of it is that it does recycle crust, and if we want to really look at things that were from a long time ago, a lot of that stuff we have no record of. So let's, again, talk about the origin of life. The one thing to keep in mind is that we have little direct evidence about the actual origin of life. We have lots of theories, but there's little direct evidence. We know, for example, that the atmosphere of early Earth, unlike today's, contained abundant carbon dioxide and some methane, but there's actually no oxygen gas. In the absence of oxygen, many complex chemical reactions are possible that lead to the production of things such as amino acids, proteins, and other chemical building blocks of life. Therefore, it seems likely that these chemical building blocks were available fairly early in Earth's history, and they would have had combined to make living organisms. And because, when these organisms start evolving, well, it starts changing the food source of what is available. For tens of millions of years after Earth's formation, life probably existed in warm, nutrient-rich seas, living off accumulated organic chemicals. In fact, it appears that the early surviving terrestrial life forms were all adapted to live at very high temperatures. When this easily accessible food, though, became depleted, life began the long evolutionary road that led to the vast numbers of different organisms on Earth today. And as it did so, life began to influence the chemical composition of the atmosphere. So, what does this mean? So, our evolution of the atmosphere. Well, if you remember, we said it was much in the beginning, much more carbon dioxide, very similar to some of the atmospheric compositions that we see in planets such as Venus and Mars. One of the key steps in the evolution of life on Earth was the development of blue-green algae, which is a very successful life form that takes in carbon dioxide from the environment and actually releases oxygen as a waste product. Now, these successful microorganisms proliferate because, there's a lot of carbon dioxide. And because they proliferate, it gives rise to all the other life forms that we kind of know now as plants. Since the energy for building new plant material from chemical building blocks comes from sunlight, we call this product photosynthesis. Anyone that has studied some basic biology knows that photosynthesis is the process in which plants produce energy. Until the presence of oxygen, and hence things like ozone, life, though, did not exist outside of the protected oceans. So the land masses of Earth in the very beginning were very barren because, one of the things is that the water of the ocean actually provided protection from the, harmful UV radiation. But once ozone was starting to be produced as a product from all these different plants, it allowed life to start to spread into the untouched landmasses. So the arrival of oxygen was a very powerful thing. Studies of the chemistry of ancient rocks show that the Earth's atmosphere lacked abundant free oxygen, actually up until about 2 billion years ago. So that's a pretty substantial time. If we think about like some of our earlier fossil evidence being at 3.5, and then we don't have any evidence of, free oxygen until about 2 billion years, that's a long time for life to primarily exist within the ocean. Chemical reactions with the Earth's crust remove the oxygen gas as quickly as it forms, because remember, there is oxygen that's present within the Earth's crust, but a lot of those oxygens chemically were removed. Now, slowly as the increasing evolutionary sophistication of life led to growth in plant production, and thus increased oxygen production. So these plants, of course, are making more and more reactions, and of course, as the photosynthesis is giving off free oxygen as a byproduct, there's now a greater composition of oxygen. And at the same time, it also appears that increased geological activity led to heavy erosion on our planet's surface. This geological activity buried much of the plant carbon before it could recombine with oxygen in order to form CO2. And because the carbon is locked up, well, now you have free oxygen molecules. Now, it's important to kind of keep this in mind with CO2, because CO2 is one of those things that's very much tied to the greenhouse effect. The carbon dioxide content of the atmosphere that we have retains heat from the sun through a process referred to as the greenhouse effect. And to understand how the greenhouse effects work, considering the fate of sunlight that strikes the surface of the Earth. The light that penetrates the outer atmosphere is absorbed by the ground and heats the surface layers. As the temperature of the Earth's surface increases, the energy is then remitted as infrared or heat radiation. If we want to trap the heat and not simply have it just dissipate back out into space, we have to have something that can do that. And the molecules of our atmosphere, which allow visible light through, are very good at absorbing infrared energy. As a result, CO2, along with methane and water vapor, act like a blanket, trapping heat in the atmosphere and impeding its flow back into space. If we want to maintain an energy balance, the temperature of the surface and the lower atmosphere must increase until the total energy radiated by Earth to space equals the energy received from the sun. The more CO2 there is in our atmosphere, the higher the temperature with Earth's surface reaches a new balance. And that is going to kind of give us a good conversation thinking about greenhouse gases themselves. Sunlight that penetrates to the Earth's lower atmosphere surface is re-rated as infrared or heat radiation, which is trapped by greenhouse gases, again, such as water vapor, methane, and CO2 within our atmosphere. The result of this is that we have a higher surface temperature for our planet. Without this greenhouse effect, the average surface temperature would be well below freezing, and Earth would be locked in a global ice age. So we actually have these gases to thank for keeping our planet warm enough to actually sustain life. Now, one thing to keep in mind, though, is that while carbon dioxide and other gases were important to keep our planet in a state that was habitable, we have to also look at this over time and see how this might be changing our planet here in the short term. Because scientists expect that the amount of CO2 that is currently in our atmosphere will double its pre-industrial level before the end of the 21st century. Now, measurements of the isotopic signatures of this CO2 demonstrate that it is mostly coming from the burning of fossil fuels, because what's one of the byproducts of burning fossil fuels? CO2. Now, evidence of climate change is apparent. Remember, climate is one of these things that we talked about where it is not a day-to-day thing, but is more of a long-term pattern. One of the things we notice is that temperature records are constantly being set and broken. Our glaciers are retreating, and the Arctic Sea ice is now much thinner than it historically used to be. We have things like rising sea levels that are also forcing coastal towns to build dikes and seawalls. And if you look at this graph here, you can see our CO2 concentration, which is in parts per million, has been steadily rising over the decades here, and it's continuing to rise well into today. Now, I already mentioned that this is coming from the burning of fossil fuels, which means humans are having a vast impact on our planet. Now, you might say, well, Earth is large, and it's been here for so long that you might think, well, humans can't really be changing the planet. We're simply insignificant specks, and we can't affect the atmosphere. We can't affect the climate. But as you saw by the evidence, This can be very surprising, though, that the carbon dioxide that we release from fossil fuels is 100 times greater than the amount of CO2 that can be released by volcanoes. Yes, volcanoes can release an enormous amount of force, but remember, volcanoes don't erupt constantly, whereas we are constantly burning fossil fuels. Everything from, running your car to, letting concrete cure, to all these different things that are, releasing gases that are going to be greenhouse gases that really trap in more heat. An even greater mass extinction is underway because of rapid climate change. As we keep changing our climate, yes, humans might be able to, in the intern, adapt to it. All other life may not have that same adaptability. And because our climate is changing rapidly, and almost all the change is a result of human activity, it means we can have some very negative impact upon our planet and its future.